Hi everybody, hope you can hear me. Just again confirm. The interface. I'm using Chrome because I don't know if you noticed that we used to be able to use Firefox, but not anymore. Yes, you can hear me. That's great. Okay. So thanks everyone for joining. I'm going to just spend the first 10 minutes at most giving a less than that, giving a very brief overview of the ARCHER2 training courses, and then we'll go into the content of this advanced MPI course. So just very briefly, all the material is available to be reused as long as you attribute it appropriately. So just a brief, what is ARCHER2? Well, ARCHER2 is currently the UK National Supercomputing Service. Unfortunately, we're currently scheduled to close the service in November. It's managed by the Research Councils and EPSRC, but it's housed, operated and supported by us, EPCC. I'll explain who we are very shortly, and the hardware, it's an HPE system. But as part of running that supercomputer, which has been going for 4 or 5 years now, we provide training, and there's 60 days per year at various locations, including online, and it's free to all academics. This training is provided as part of the ARCHER2 CSE team's training offering under ARCHER2. So we're going to be using ARCHER2 for the exercises. This isn't a course on ARCHER2. Sorry, this isn't a course about ARCHER2. It's a course about advanced MPI, but we'll do some exercises on ARCHER2. This is a mock-up of ARCHER2. I like this picture better. This is what it looks like now, but it's not particularly exciting because it's just, well, I've got nice pictures on it, but you can't see it. But in the early stages, we had an initial system, which was ARCHER2, I think, is 23 cabinets of processors. We had an initial development system, which was only 4 cabinets, and this is a picture showing the back of it off the back, so you can see all the wiring and such. I quite like that picture. This is a Cirrus system, which is the reason we replaced. We're not using that. We use that for some training, but not this course. I've mentioned EPCC. You may know what is EPCC. We're now the UK's National Supercomputer Centre. We've been around for over 35 years. Originally, it was called the Edinburgh Parallel Computing Centre, but technically we're just EPCC. We're part of the University of Edinburgh, and we've been running national parallel computers for over 30 years, since the first Cray T3D national parallel computer system in '94, and we'll be hosting the next national supercomputer system in a couple of years' time. But over 100 of us, we do academic and commercial projects, and also postgraduate teaching and HPC training courses. I'll mention that very briefly. The reason I mention this is if you come to this course, and that's very interesting, but I'd like to collaborate with the EPCC afterwards. How do I do this on my research project, for example? In terms of UK research project, EPCC staff members are just standard postdocs, research assistants. So a lot of our staff work collaboratively on research projects with groups around the UK and in Europe more increasingly. And they just named us 50% on somebody's research grant. That's a lot of joint research proposals we do on the academic side. This course isn't in Edinburgh. This is a picture of Edinburgh. If this was an in-person course, you'd see this. It's not as sunny as that today. There are lots of ARCHER2 resources, but as I said, this isn't a course about ARCHER2, so hopefully I've shrink-wrapped the exercises, so even if you're not really an ARCHER2 user, having got on to ARCHER2, and I can help you do that during the first practical session if you're having issues logging on, having got on, then you can run these exercises. I would say some of you may have your own accounts, but you will have been given accounts, hopefully, as part of this training course, TA1241, I think it is, the project. For the exercise, it's better to use those training accounts because you have access to a dedicated set of CPU resources which are reserved, at least for the morning, which allows you to do the exercise. I mean, you can run in the short queue, and you'll probably get the exercises run in reasonable time. But I have dedicated resources which will guarantee, and the scripts are set up to use those resources. Who am I? My name is David Henty. I'm in overall charge of education and training at EPCC. I'm involved on our on-campus RSC programs and the ARCHER2 training program and commercial training. My research interests are kind of in just general parallel programming models, performance, and parallel I/O. Other resources, there's a general help desk, but the main thing is please fill in the feedback form. You'll be sent a link at the end of the course to fill that in. As I always say, good feedback from users is great. It makes us feel good about ourselves, and we can say how wonderful we are to EPSRC. But also, critical feedback, we do read and review all the feedback at regular meetings. So we do take feedback seriously and try and take it into account when designing future training programs and future iterations of these courses. I'm just a bit of a plug here. It was a bit late for this year, but we run a one-year postgraduate master's course. This material actually comes from originally a course I gave on the MSc a few years ago. I don't give that course anymore, but it's originally MSc material. We've been running it since 2001, MSc and HPC and MSc and HPC with data science. We have an on-campus and an online version. This is some graduates from a few years ago. It's a standard UK one-year MSc. You can do it part-time, but most students do it full-time. Taught courses and then a research dissertation. During the course, we've given you personal accounts for the duration. They'll be around for about a month. After the access ends, the files will be closed and then deleted. So the main things I would say, if you do, there isn't that much programming on this course, but if you were to do some programming or did stuff on ARCHER2 in your training account, please take a copy off today. I mean, you'll be able to have a month to take it off, but it's easier to take it off today. However, don't worry about the material. The material will be on the ARCHER2 website for the foreseeable future. Longer term, now, as I said, unfortunately, ARCHER2 is currently scheduled to go away in November. But if you do want to get on, I think, Claire, we are still giving accounts under the driving test. So if you went away and said, well, I'd like to get back onto ARCHER2 to play around a bit, do a bit of tests, maybe try my own programs, you can take the driving test. It's just simple questions to check you've read some of the documentation, and you get 800 compute units for up to 12 months. Obviously, that will be curtailed if the system does close in November. But 800 compute units is 800 node hours, which is about 100,000 CPU hours. It's quite a lot of time. This isn't relevant. We're not teaching live at the moment. We'll have a code of conduct. So, just to let you know, if there are any issues about my behavior or other people's behavior, then please feel free to report it there. And I hope you enjoyed the course. Please ask questions. So I'll give a brief overview of where this course is coming from just now, but please ask questions, because the slides will be up for the foreseeable future. You'll have access to the material. We are recording this. So the recording of this session will also go up. However, the advantage of having a live, even if not face-to-face, but a live synchronous course is you can ask questions. So, okay, that's working now. So this is the ARCHER2 web page. If we go to training, you'll see there's an upcoming training, and there's the advanced MPI, which we're on just now. And there's a brief overview here, but the main thing is there's a course materials link here. And so this is the schedule for today. We're a bit on time. I'm going to talk about some internals of MPI, how does MPI work internally, and then we'll have a practical to do with point-to-point performance, then a quick coffee break. So I've split the practicals around a coffee break. If you are having any problems logging on, I can give you help here. That gives us plenty of time to give a help. Then I'll talk a bit about MPI optimizations, what you can do to try and make your code a bit faster. And then I have a practical, which is basically to do with, I have a halo swapping example, which you can play around with. In the afternoon, I'm going to talk about advanced collectives and the MPI shared memory model, which I'll talk about. I'm doing worked examples there. There's not really time there, but I'm going to work through the solutions there. So what I was going to say is previously this course was about 2 days long, but I felt like too much material. So the last couple of times I've asked people what they're interested in, and before I gave the course, had a little survey, and this was kind of what people seem most interested in. It is a bit of a, it's a fairly, I wouldn't say random, but it's just a selection of topics that I think might be interesting. But that's why I say, there is other, if you have questions outside of the course about MPI, please ask them, because I may have material I can chat about it. But I felt these were topics which I've found people are interested in, and also from being on the ARCHER2 help desk and such like, these are things which are useful to people. Okay. So the first thing I'm going to do is talk about, and these are links to the material, and there's exercise material down here. I've pulled an exercise. I'm going to talk a bit about MPI internals. So that's the first talk. So I will hopefully. Okay, so that seems cool. So you can please ask questions if you have. It's probably easiest if you by text via chat. So I can see the chat window there. So if there are, if you do, please feel free to. I mean, if we have an extended discussion, we can maybe use audio. But just for the brief question, please ask via the chat. So okay. So I'm going to give a brief overview of MPI. If you may have been on an MPI course, you may have been on the MPI course that we give as part of ARCHER2. The library, MPI library, is given as a black box. You call send, you call receive, it all happens magically. However, it is useful to have some understanding of what goes under the hood, both in terms of writing correct programs, but here in how you can, if you know a bit about how MPI is actually implemented, then you can understand more about the performance of your programs and hopefully maybe even make decisions that allow you to write faster, more performant programs. So I'll talk about the MPI library structure. I'll speak mostly about point-to-point, a brief bit about collectives and more and groups of communicators, but and the single-sided I won't really cover for various reasons. But really, this is really about the MPI library structure and point-to-point communications. The way that point-to-point communications work in MPIs under the hood is slightly more complicated than you might imagine, and understanding that can be useful, and we'll have a performance exercise there. So, like any large software package, MPI is divided, the library is divided into modules, but actually the natural split is to follow the MPI standards. The MPI standard has chapters on point-to-point collectives, groups and contexts and communicators, process topologies, process creation, one-sided and MPIO, at least the earliest versions of the standard. There's a lot more in there now. And so a standard MPI library, if you download an open source MPI library, you will get probably directories with source code appropriate for each of these topics. There may be hidden internal modules. So for example, MPI implementations are written to be portable, to be able to take an MPI library and implement it on different hardware. And so what a lot of a standard approach is to have most of the code is hardware independent, but to have a small piece of code which is hardware dependent. And so that often involves access to the network. How you access the network may depend on what the network hardware is. Is it Ethernet? Is it InfiniBand? Is it something more bespoke, like the Slingshot network on the HPE systems? And so there may be an abstract device interface. There may be some module which handles all the network traffic, but the majority of the code you'd expect to be hardware independent. And when developing the library, you'll try and isolate all the hardware dependent parts to a very small kernel of routines, which you then have to port if you want to take the library to a new platform. So point-to-point communication is the core of most MPI implementations. Collectives are, so if you call it MPI reduce or MPI all reduce, they are usually built from point-to-point calls. Not necessarily, we'll come back to that, but they often are. MPI I/O, if you do I'm not going to cover parallel I/O in this course, but if you do use MPI I/O, most MPI libraries pull in something called the Romeo implementation of MPI I/O, which is an implementation of MPI I/O that just calls standard MPI. So so again, if you have the point-to-point send and receive implemented robustly and efficiently, then most of the other parts of the MPI library will work well. There are a large number of point-to-point calls, which there are a number of ways of sending messages. There's synchronous, there's asynchronous, there's blocking, there's non-blocking, but these will probably be implemented from a simpler set of functions in this abstract device interface. So we'll come back to that. So, but what we're going to do when we do the the message passing exercise is a ping pong. We're going to basically take two processes, and they're going to send and receive data to each other continuously. And what we're going to try and do is understand try and predict, or at least understand what the performance profile of that. How does the time taken to send two messages to send a message between two processes depend on things like where the processes are they on the same node or different nodes? But more fundamentally, how does it depend on the message length, how much data you send? And that dependence isn't as simple as you might think. But the simple performance model, the thing you have in the back of your head, is, I think, best illustrated by a car analogy. I'm not mad keen on cars, but I always think cars and travel are very, very good analogies for parallel computing. So the analogy is, I have a car journey, okay? And so my car is parked in a nearby garage, so it takes 5 minutes to walk there. Doesn't matter where I go, okay, where I travel to by car, it always takes me at least 5 minutes. And that will turn out to be equivalent to the latency in message passing. After that, let's say I average 60 kilometers an hour, which is about, just under 40 miles an hour when driving. And that speed of my car will translate into the bandwidth of my network. But here I'm using an analogy, which I think is more easy to get your head around. And the question is, how long does my journey take? What is my average speed? So clearly, the time taken for a journey in minutes against the distance in kilometers always takes 5 minutes, regardless of the distance, but then increases linearly because I'm driving at a constant speed. To go twice the distance takes twice the time. Or I can look at my average, or I can plot that on a log plot, and it looks like this. It's the same plot, but on a log plot. Okay, so that's the time. How does my time vary with distance? But you see that you have small and large distance behavior. So I can also I could plot the time against the distance, and you can see that for distances up to about 1 kilometer, or here about a few kilometers, the time is relatively constant. So if I make a small journey, not surprisingly, the time it takes to take a small journey is dominated by that 5 minutes it took me to walk to the garage. Okay, 5 minutes to walk to the garage, get in the car, and then drive away. So I have small. So for small messages, I have constant time. Then the time starts to increase. But if I don't plot the time, I plot my average speed. And so this is equivalent in a network context to plotting the bandwidth, the megabytes or gigabytes per second. You'll see that what happens is that for small distances, I have a very small speed, but for larger distances, I end up with a constant speed. Okay, I approach this 60 kilometers an hour quite as a plateau. And so you can see the important point here is there is small and large distance behavior. Small distances takes a constant time. Large distances achieve a constant speed. And where is that crossover? Well, a very, very useful metric is n.5. This is the number of kilometers you have to travel where you take the equal time driving as walking, where it takes 5. So the switch over between small and large distance behavior happens round about the journey length, where the journey is 50-50 split between the walking to the garage and then driving. And so that is so n.5, the distance which is the boundary between small and large distance behavior is 60 kilometers an hour times 5 minutes, which is 5 kilometers. So below 5 kilometers, my journeys take constant time. Above 5 kilometers, my journeys start to go to work at constant speed. And the analogy there is for point-to-point MPI, or for data being sent over a network. The latency is the overhead of sending it. Now, it's slightly confusing here, because I think if you come from I actually have a computational physics, a computational science background. But if you're a computer scientists tend to use latency to be the total time it takes to send any message. That's not what we're meaning here. The latency is the overhead. The latency is the overhead you pay of the equivalent of walking to the garage. The overhead of sending any message. It's the time to get a very short message, a 1 byte, 0 byte message onto the network. And a typical number there and we'll measure what this is when we go on to ARCHER2, but a typical number is about a microsecond, it is measured in microseconds. The bandwidth, which is what the manufacturers like to quote to you, because it's a nice big number, is the rate of transfer on the network. So it is if you send a really, really big message under ideal conditions, how fast parallel computer where the latency per second and the bandwidth is 10 gigabytes per second. Here I would say n.5, this message length, which distinguishes the small and large message behavior, is 10 kilobytes. And if you actually plot the time it takes against the message size, you will see at 10 kilobytes, we go from constant time to rising time, or significantly above 10 kilobytes, we start to approach constant bandwidth, which here would be 10 gigabytes per second. And we'll plot these graphs, time and bandwidth against message size for real messages. But you will see you get behavior which is analogous to this, but there's a lot more detail going on. There are thresholds, there are barriers, there are drops, and there are jumps in it. And what we're going to try and do is, this is your theoretical textbook model for how the message time, how the time taken to send a message of n bytes would vary with the size of the message based on the latency and the bandwidth. In practice, it'll be a bit more complicated than that. But hopefully, after this rest of the talk, we'll be able to understand where that complication comes from and what it corresponds to. So MPI has multiple types of send, and this is where MPI is slightly confusing, maybe more complicated than it need be, but it's historical. When MPI was defined back in the early 90s, there were lots of other message passing libraries out there, and some of them used buffered send, some used sync. So a buffered send is what MPI calls an asynchronous send. If you do a buffered send in MPI, the buffer send completes locally whether or not a matching receiver has been posted. It's like sending an email. Okay, so when you send an email, you say, here's a message, send it. It then it's a fire and forget. Okay, so what happens? The copy is taken of your email and sent to whoever you're sending it to. That's the same as what happens in a buffered send, MPI B send in MPI. The data is buffered, a copy is taken of the message, and then it is then sent later. And so the advantage is you don't wait around for an asynchronous or buffered send in MPI. You don't wait around for the receive to be posted. The two downsides are you don't know if and when that message is actually received, and secondly, it will fail if sufficient buffering space is attached. It's a bit, the way MPI works for buffered sends is a bit nasty, but basically if you have to say to MPI has to reserve that amount of sufficient buffering space to do buffered sends, and if you try and send a message that is too large, MPI will fail at saying I don't have enough space to buffer it. Synchronous send is more like making a phone call. Synchronous send is only complete when the match and receive have been posted. So sending an email, you can post the email, you send it, and it goes off, and you don't know if you don't know explicitly when someone has read it. When you make a phone call, that's synchronous. You pick up the phone and you wait for someone to issue the receive, i.e. for the receiver to pick up the phone at their end. So MPI to synchronous send if no receive the synchronous send wait. The upside is there's less buffering. There's no need for copy of intermediate messages. So there's pros and cons between the two. MPI also defines something called a ready send, which I don't actually cover anymore in my MPI course because it's only there for historical reasons. It actually assumes that a receiver has already been posted. I've never seen anyone use a ready send in a real code, but it's just there for historical reasons. The point of these slides is, and I cover this in my MPI course, what is slightly confusing in MPI is that most people program using the standard send, which is MPI send. Where MPI is slightly confusing is the MPI standard does not define whether standard send, MPI send, is buffered or synchronous. It allows MPI to choose. If you do an MPI send, the party line is the MPI will decide, according to a certain set of criteria, it will decide, okay, David wants to do an MPI send for this message. Will I send that synchronously, i.e. wait for the receive to be posted, or will I send it asynchronously, do a buffer send, take a local copy? And you don't know which it does. That makes MPI surprisingly confusing in this respect. And you shouldn't assume whether buffering takes place or not. But the reason I mention this is the fundamental way where MPI tries to optimize the performance of sending data between two processes. It will decide based on the message size whether to do a buffered send, take a copy of your message, or to do synchronous send where it doesn't take a copy. And we will be able to see the effects of that decision in the time, the bandwidth and the latency, or the bandwidth and the message time when we do the ping pong test. So one of the reasons that MPI is slightly confusing here is that MPI actually requires a certain amount of quite restrictive behavior for messages. It requires that messages are ordered. Messages sent between two endpoints must be non-overtaking. And so when you if you issue a receive and there are multiple messages that it could match, it will receive them in the order they were sent. Now this is a restriction on MPI because of course modern networks don't. A modern network is not does not preserve message ordering. And modern networks use these packet switching, and messages divided up into lots and lots of different packets, all of which can take different routes. So at the hardware level, if I send if I transfer data over the network at hardware, that the order of those two transfers is not preserved. However, MPI has to guarantee that the messages ordering is preserved. Now, actually, it's actually quite subtle. If you look, even if you've never been aware of this, most programs implicitly rely on this. If two messages could overtake each other, most programs would not work. For example, you send a message, then you send a message saying that's the last message I'm going to send. If they overtake each other, your program breaks. And so actually message ordering is very, very important. Fairness, MPI does not guarantee fairness. This is things like, for example, if you do a receive from MPI any source, MPI doesn't guarantee that it will fairly pick if there's multiple messages in the network. It doesn't guarantee it will even them out. But a good MPI implementation will do this. A good MPI implementation will try and be fair. That if each time if you if your wildcard receive from MPI any source, that it will try and balance the load. But the main thing which causes this restriction on MPI is resource limitation. There should be a finite limit on the resources required to process each message. So this means that if you think about MPI send, the standard send, which in MPI is MPI send, is allowed to be synchronous or asynchronous, allowed to be buffered or non-buffered. You might like MPI to always buffer it. You'd like, well, I just want a message to be fire and forget when I send a message. I would just like MPI to buffer, take a copy of every message I send. That MPI cannot guarantee to do that, because then it would violate this constraint. There should be a finite limit on the resources required to process each message. What that means is you could basically keep issuing multiple MPI sends, and MPI would have to buffer them all, and the memory requirements could grow infinitely. Okay, and so that's why MPI cannot guarantee that every standard send is buffered, but it will try and buffer them. We'll come back to what implications that has on the protocol later on. Another thing is progress. I've got an exact example. Outstanding communication should be progressed where possible. So actually, what this means is if you call an MPI receive, in your mind, you might think that what's happening is MPI is sitting there waiting for a message to come in. To make MPI work correctly, that's not what's happening. When you call an MPI receive, MPI will check for an incoming message, but if there isn't any, it will use that opportunity to go and do bookkeeping. And so basically it will do lots of other stuff. So every time you call an MPI call, okay, MPI eventually will get around to doing what you want it to do, but it will use that as an opportunity to go and do bookkeeping to keep things ticking along. And so outstanding communication should be progressed where possible. That means that often calling an MPI call, MPI goes away and does lots of other stuff first before it actually gets around to doing what you wanted it to do. And as I said, these all influence the design of MPI implementations, but in practice, the one that we're going to see most often, that we're going to have the biggest effect is the resource limitation. MPI cannot guarantee to take a copy of, to buffer every standard send, MPI send, and so it has to have an alternative approach for large messages. So this is message progression. You may not have thought about it, so I'll go through this, a slightly contrived example, but so rank 1 sets up a non-blocking receive for an integer from rank 0. So rank 1 is saying, I'm expecting a message from rank, but this is a non-block. So say in the future, I'm going to be expecting a message from rank 0. Okay, and then it goes on and calls a barrier. Okay, so it's sitting in a barrier. Let's imagine sometime later, rank 0 issues a synchronous send to rank 1. So rank 0 issues a sync. So what's going to happen here, if rank 0 is sitting in this is synchronous send, so rank 0 is sitting there, and rank 0 will not progress, okay, until the receive is matched. Now, if, for example, rank 1 issues this statement very early, okay, apologies. If rank 1 issues the standard send before, if rank 0 issues the standard send before rank 1 issues the receive, there will be no problem. Rank 0 is issuing a standard send, rank 1 issues the receive, it sees the incoming messages and they match. The problem here is if rank 1 is quick. So rank 1 issues the, rank 1 issues the receive quick early and then immediately sits on a barrier, okay? Rank 0 is stuck in this MPI send. So we look like we've got a catch-22 here. Rank 0, if rank 1 did nothing but sit in the barrier, it will be waiting for rank 0 to arrive, but rank 0 is waiting for rank 1 to process this outstanding non-blocking receive. So what is actually happening is, in rank, when you call a barrier, rank 1 is not just sitting there waiting for everyone else to arrive. It is periodically checking if people are arriving, but while if other people haven't arrived, if rank 1 has not arrived if rank 0 has not arrived in the barrier, rank 1 is going away and checking, and eventually it will notice, oh, there's an incoming message from rank 0 standard send. I will process that and match that with my receive. So this is just basically to show you your mental model of how MPI works may not be how it actually works. So often people's mental model of MPI is that it's a universal, always running postal service. It's not. Most MPI implementations are single threaded. That means that the code is either running the MPI library or it's running your code. And so if it has multiple, if there's outstanding MPI operations to take place, they can only be processed when it's in the MPI library. So what MPI does is it effectively uses every MPI call as a kind of a manual interrupt. You call MPI and MPI goes, great, now I can do all my bookkeeping, I can do all the progress, all the outstanding stuff that's going on, then I'll actually do what David asked me to do, okay? So that's just so it's a bit subtle, but the real, and the other choice you have is not only do you have the choice between synchronous and asynchronous buffered send and synchronous send or standard send, you also have non-blocking operations. So you can also tell MPI to issue a non-blocking call, which says don't do this message passing operation, be it a send or receive immediately. It's a request saying, I want you to do this sometime in the future and get back to me, and I'll come back later on to see if the message has completed. And so MPI defines both blocking and non-blocking calls. In fact, at the very, very lowest level, most networks are actually non-blocking. Most networks are non-blocking in the sense that when you initiate something and check for it to happen later on. And so actually, most implementations implement blocking messages as a special case of non-blocking. That's just a bit of an aside, actually, but it's worth knowing that actually at the hardware level, most networks are non-blocking in the sense that when you send data, you don't say, please send this data and I'll wait for it to be transferred. You ask the network to send the data, and later on you come back and check whether it's been sent. And so just to say, this is the standard example of how you use non-blocking operations. If you want to do a halo swapping between up and down neighbors, I issue a if I did this in a blocking way, if I called MPI receive and if MPI receive here, the code would block, because this receive would wait until the send had been posted, but the send is down here, okay? So if you wrote this with blocking calls, MPI receive, MPI send, MPI send, this would be guaranteed to deadlock, because these receives are waiting for the sends to happen, but they never happen because everyone's sitting in the receive. And so we use non-blocking here, which we post. We say, I'm expecting a message from my up neighbor, I'm expecting a message from my down neighbor, and then I can then get on to sending my messages. I'll send down and up. And this is slightly subtle here, that actually you want this send, you want these to match correctly, and in fact, to ensure correct message, to make sure that that send down matches this receive, this receive up. You want the send down to match the receive up. That does actually require message order preservation. The fact that that send down is guaranteed to match this receive and not that one takes advantage of message order preservation, which again may not be entirely obvious, but it does. MPI also defines persistence. What I'm doing is I'm running through the different kind of different ways that MPI has for doing send and receive, which you may not have been aware of. You've probably been aware of non-blocking communications, may not have been persistent ones. MPI also defines persistent communications. When you write most MPI programs, you might have a loop which is executed hundreds of thousands of times. And in that loop, you send some data up the way and receive some data down the way. Every single MPI call is identical. It has the same neighbors, the same data size, the same pointer to the array, okay? And so it seems a bit strange that you have to call that many, many times. If you're going to be executing exactly the same MPI call with identical parameters multiple times, it might be useful to tell MPI, look, I'm going to be executing this send or receive call thousands of times. Maybe it can then go away and do some optimizations. And these are all persistent communications. They act a bit like non-blocking communications. They can be run many times. So what you do is you have a two-stage process. You first define what the MPI, you tell MPI, I'm going to be calling this routine with these arguments many, many times. Then you get back a handle, and then later on you can tell it to do it. They're called persistent because they're executing the same message passing call multiple times. Now, the reason they were not particularly heavily used is that in the initial incantations of MPI, there were only persistent point-to-point calls. And in practice, MPI can't make much use of that. The fact that it knows you're going to call the same MPI send routine 1,000 times doesn't really help it. However, there are many, many more optimizations possible in collectors. Collectors are a lot more complicated. For example, depending on the parameters of the collector, the buffer sizes, or the number of processes, MPI may want to use completely different algorithms to implement those collectives. And so knowing you're going to call the same collective millions of times is useful. And in fact, persistent collectives were introduced in M 4.0, which is probably, I say recent, probably about 15 years ago. So the reason you may not have heard of persistent communications then, they were fairly hardly ever used, but they might be useful in investigating. In principle, MPI, if you tell MPI you're going to run this collective thousands of times, it can go away and say, okay, David is going to be running this collective routine thousands of times. I can go away and spend some time making sure I'm doing that the most optimal way. So that's persistence. So the way that point-to-point persistent calls work is that, if I use the same example here, instead of doing the receive call, you call MPI receive init with all the same parameters, and that doesn't perform the receive. It tells MPI, I'm going to issue this sometime in the future, and you get back a request handle which identifies this persistent communication. So rather than in the example I showed before, sorry, I'm getting a bit of here, I call the receive, I call the receive, I call the send, I call the send. With persistent collective, you say, sometime in the future, I'm going to call this receive, I'm going to call this receive, I'm going to call this send, I'm going to call this send, but you get back these requests, and later on you say MPI start all. You say, I'm going to start, I want you to start all these requests. I want you to issue a receive, a send, and then these are actually issued in a non-blocking way, and you have to wait for them at the end. So again, they're not particularly useful, and it turns out they're not particularly useful in practice for point-to-point operations like this, but they can be useful for collectors. Just a subtlety, the order of individual calls is not guaranteed here, so you may need to be more careful about your message matching. Hopefully, when you program with MPI, you use derived data types. MPI defines a rich set of derived data type calls. There are really sort of two different reasons for using derived data types. One is if you want to send data which are things like data types which are defined at runtime. So for example, in C, that might be a structure. And so you can define MPI data types which allow you, if you have your structure, you can send 5 of those structures, for example. And so MPI predefines various basic data types, MPI int, MPI double, MPI byte, and things like this. But at runtime, you can define your own data types and then send and receive them natively. However, you have to be aware of there's no magic going along here. As I said, at the very low level, your MPI library will have some abstract device interface, some subset of a small number of routines which map directly onto the hardware. And what they'll possibly will be allow you to send and receive n bytes. That will be the lowest level call. And so to implement the send of a derived data type probably at some level involves copying. What MPI probably does when you ask it to send a derived data type is to take a copy of that into some temporary buffer, send or receive it as a bunch of bytes, and then do a copy back at the end. Okay, and so when I teach my MPI course, I say to people derived data types are nice because they avoid you having to do copy in, send, copy out. You can directly send and receive these higher level, more complicated data types. Under the hood, MPI is probably doing the copy in, copy out for you. However, it's more elegant. You might argue that your own copy in, copy out might be more efficient and be worth doing, but that's worth knowing. It may be actually that if you're doing very simple strided patterns, so for example, rather than sending 4 integers in a row, you're sending 4 integers at location 0, not location 0, 1, 2, and 3, but location 0, 2, 4, and 6 strided data. It may be if you define a derived data type for that strided pattern that it may be able to send that natively. It may not need to do copy in, copy out. The network may support strided data transfers, possibly. But the mental model you should have is that the way that MPI implements a derived data type is through a copy in, copy out. But that is done transparently to you. And so they are more elegant to use than explicitly doing the copy in, copy out yourself. So that's really just a bunch of a bit of a butterfly collecting of different aspects of MPI. I'm now going to go on to the actual part which talks about how MPI implements the send and receive, what protocols does it use under the hood, and this is linked directly to the exercise where we'll run a point-to-point send and receive. But it was a bit of a butterfly collecting. Are there any questions about that first half of the talk or 2/3 of the talk? Just quickly, the thing which maps most, which is most applied and match most directly to the exercise is what we're going to go on to now. But if there's no questions, I'll just carry on with the next part. So fundamentally, an MPI implementation needs two mechanisms for delivering packets of data to a remote process. Okay. Now, these may be your messages, or they may be internal protocol messages, bookkeeping messages sent by MPI. But fundamentally, MPI needs to be able to send n bytes of data from process A to process B. Okay, and these are generic. So what your MPI implementation does will depend on the detail. But this is a generic model which is useful in understanding how they work. It's probably how most are implemented. Whenever your process sends an MPI message to a remote process, MPI will send a protocol message. Okay, so it will send a little header saying, if I issue a send of 1,000 bytes, the first thing MPI will do will send a little header message saying, David wants to send you 1,000 bytes. Okay, so it will send a little header message to the receiver saying this is to give it advanced warning of what it's expecting. Okay, and so minimally that will just contain the envelope information. It will just say, if I do an MPI send of 1,000 bytes, there'll be a little header message go off to the receiver saying, by the way, Dave is trying to send you 1,000 bytes. You're going to expect it in the future. It may also contain some data. We'll come back to that. But your model is it's an initial contact. I'm going to send you some data. Okay. Many implementations use a fixed header size for all messages, and typically they always do. So maybe like 100. So in your mind, you should think whenever I send a message, the first thing that happens is a little header goes. maybe 128 bytes, is sent over, and that will have various fields in it saying what that receiver is going to have to expect. Okay. So as I said, there will be initial protocol messages sent over whenever you do a send. Okay. So on the receiver, okay, I get I'm a receiving process. I get a little message saying Dave's expecting to send you a message. Okay. I may already have actually issued a matching receive. So if I say, oh, Dave's telling me, oh, there's a receive waiting here, I can then get back and say, send the data, okay? So if the receiving process has already issued a matching receive, the message can be processed immediately. However, if it's not, I have to store it's called a foreign send queue. I have to say, okay, this guy's trying to send me a message. I don't have a matching receive, so I have to park it for the moment, okay? So that immediately tells you that it's good MPI programming practice to issue the receives as early as possible. That means when the send comes in, it can be matched immediately. Similarly, if I receive a receive call, okay, the first thing if I issue a receive call is, or maybe somebody's already trying to send me a message, okay? So when I do issue a receive call, I look in the foreign send queue to say, okay, I want to do a receive. Has anyone already contacted me with the matching receive? If they have, I can process it immediately. If not, I have to put this into a foreign send queue. So the foreign receive queue is for, it tells you people who are trying to send data, you don't have a matching receive. The foreign receive queue is receives you have issued, which don't yet have a matching send. There could be lots of queues for different communicators or senders, but in practice, most people have a single global queue. Because there are times you're going to have to look through these queues, because when you do wildcarding, you're going to have to look through them all. And so, again, you have to be careful not to send lots of messages and never receive them, because these queues can get very large. And on ARCHER2, you sometimes get, if people write programs where they send lots and lots of messages and the receives don't keep up, once you get to a few thousand messages coming in that haven't been received, there's an internal error. And MPI says something like, I can't cope. I don't have enough room to buffer all these things. So but that doesn't often happen in correct programs, but it can happen. So MPI implementations will use different underlying protocols depending on the size of the message. And so basically, I said that. Well, I'll just fry the protocols first, and then come back to how this matches, how this is implemented for MPI send. So the two ways that most MPI implementations will send data between two processes, and there are two protocols. One is eager and one is called rendezvous. There's lots of variants on these, but if you understand how eager and rendezvous work, then you've got a good mental model for how MPI sends data, and then you can try and understand any performance issues you have in terms of this. So the eager protocol, okay. In the eager protocol, when you want to send data, you eagerly send the data. So what you do is you send a message saying, I want to send you some data, but you also send the data itself, okay? And this means that the data has to be buffered at the receiver. So in the eager protocol, whenever you send a message, you basically send the data as soon as the data is the send call is issued, you send the data regardless of whether the receiver has been posted or not. Now, clearly that requires the receiver to have some buffer space to store those. So clearly this can only be done for small messages, okay? But for small messages, okay, what MPI will try and do, it will send them eagerly. It will send the data over. It will be stored somewhere on the receiver, and that send will complete immediately, okay? So the eager or the buffered or standard sends can complete as soon as the initial protocol message has been sent. So this means that small messages in MPI can typically go faster than large messages because they're sent straight away, copied to the receiver, and then you carry on. For synchronous send, there's a slight subtlety that the synchronous send, you need to know when the message has been received, so there will be an acknowledgement sent back. But the fundamental point about the eager protocol is the eager protocol eagerly sends data. As soon as you issue a send, the data is copied to the receiver. Okay, and so I found a nice diagram for this from a course at Belgium University. Okay, what happens here is that when you issue the eager protocol, so this is nothing to do with MPI definition of how MPI send, send, send work. It's how it's implemented at the library level. What happens is when you, and this happens for small messages, when a send is issued, it's copied to an intermediate buffer, and when the copy has been happened, then the sender just carries on its merry way. Okay. What happens on the receive side is when the receive is issued, it knows the data has been, it doesn't have to copy the sender, it knows the data has been copied. This MPI buffer is actually on the receiver, and then the receiver can do a final copy. Okay, and this sounds like a really good thing. This sounds like a really nice thing to do. Basically, whenever you issue a send, it acts if it was asynchronous, it acts as if it was buffered. The data is sent over to the receiver, regardless of whether the receiver has been issued, and you carry on your merry way. And then when the receiver issues the receive, the data is actually copied into the receive buffer. However, this cannot be what happens all the time, because if you send a really large message, if you send a gigabyte, there's no way the receiver is going to be able to store multiple messages of a gigabyte. So for large messages, in practice, you need to do a different protocol, and that is called, so the resource constraints, apologies, the eager protocol requires buffering the receiving process. This violates the resource semantics that we have to have a finite amount of resources associated with the MPI. And so that basically we can only do the eager protocol for small messages. I'll skip the statement about ready messages here because I've decided that ready messages are not something to talk about. So for small messages, we try and use the eager protocol. What do we do for large messages? Well, in the rendezvous protocol, the initial protocol message just contains the envelope information. It just says Dave is trying to send you a message. Okay. However, so when this is matched, the receiver gets back to the sender and says, I'm now ready to receive the data. And then the data is sent. And so it's called a rendezvous because there's a there and back. And we'll see that in the diagram in the next slide. Okay. So the send acts as a synchronous send. When you issue send, you send a little message, I've got data for you. You wait until the receiver is posted, the receiver gets back to you, then you send the data. In fact, you might think so there's clearly some handshaking there, which it adds time, adds latency. However, for large messages, that can be more efficient because you don't have any intermediate copying. So there's a trade-off between the latency, which is the handshaking overhead, and the data transfer, where this allows you to avoid copying. And so this diagram is useful when if the sender calls an MPI send and the data is large, MPI will decide to do that synchronously. It sends a send request. When the receiver issues a receive, it says, okay, you're ready. I'm now ready to receive. The MPI then sends the message over and the receiver gets back saying, I've received it. So you can see there's a lot of toing and froing here, as opposed to a single message operation, okay, which this data is going over the network to the remote buffer. There's a single there and back here. Here we have double there and back. So naively, you might say this would have twice the latency. We can see if that's true, but that would be your initial guess. And so what actually happens in reality, if you send messages with MPI send, you will see two regimes. One where the message size is small and MPI can use the eager protocol, and that is more efficient because it has less latency. But at a certain size, MPI says that message is too big, I have to use the rendezvous protocol. You will see a step up in the time, and then that's when, and you can see this threshold in the when we do our point-to-point message, when we do our ping pong example later on. There are other protocol variants. The obvious one is the very short message. I said that typically a header has maybe a fixed size, 128 bytes. So imagine I want to send a single integer, okay? What I could do is I could send the protocol message saying, David wants to send you a single integer. Later on, the receiver is issued, the receiver gets back, then I send it one integer. Well, there's probably enough room on the header messages for very short messages. So for very, very short messages, okay, you have an optimization where the data goes with is it put on the header. So There's a very good question from Blair. I'll come back to that. This is like sending a postcard, okay? When you're on holiday, you're typically sending small messages, very short messages. So a postcard, yeah, a postcard is like a protocol message, but it has a letter. You split. The letter has an envelope with the header information on it and the contents inside. For very short messages, which you can fit on a postcard, you get away with that, and you just send a postcard which has both the header information, the envelope information, and the data. And so up to a few tens of bytes, you can probably fit that. Now Blair's asked a very, very interesting question here, which is, does the threshold? Yeah. So in principle, yes. So I have seen systems in the past where, so the obvious thing is to reserve a buffer for an eager message from every possible source. Yeah. So when MPI starts up, it will say, okay, I want to be able to support the eager protocol. I need to have somewhere to put messages which were sent to me. So I will instantiate a buffer. And it turns out that buffer is typically about 10K or something like that, a 10K buffer to receive a message from every possible sender. However, if you run on large numbers of processes, that will start to get too big. So in principle, MPI might scale down the eager limit on large process counts. I believe that is true. However, I've never seen that in practice because for a ping pong, which is the standard test, you're only running between two processes. But yes, in principle, the threshold scales with resource available to the system. If I have more memory, can I send like also well, probably MPI has a default. However, you can alter that default by some magic variable. So definitely on HPE systems, you can tell MPI, I would like the eager limit to be larger, but it will only do that if it has the appropriate resources. Does that answer your question? But it's a very good question. I think by default, it probably doesn't. It probably has a fixed amount, which will actually make smaller if it runs out. But you can ask for a larger amount by changing some magic environment variable, which I think I mentioned in the exercise sheet. Yeah. So yes, you can increase the eager limit yourself, but MPI will probably ignore you if it thinks you're asking for too much. Does that answer your question? I've witted a bit there, but yeah. No, okay, yes. So yeah, again, in principle, now all this is under the hood. So in principle, MPI does a whole bunch of things. In practice, MPI reserves a buffer of fixed size for all eager messages. Okay, so no, it's not dynamic. In practice, it just issues a fixed buffer. However, you may be able to affect the size of that. Direct memory access protocols, some message passing networks actually allow for data to be transferred directly from the sender's memory to the receiver's memory with no copying whatsoever. That has a lot of sense. So there may be for very, very large messages, there may be a third protocol where MPI does a direct memory access. It does a lot of setup and does direct copy. But yeah, it's hard to see that often. We use non-blocking receive, but we manually input eaglet programs to be used by default. No, so that's not true. So whether eager is used is depending on the sender. So if you use a non-blocking receive, okay, so it's the sender which decides whether to use the eager protocol or not. So the sender says, if it's a small message, I will use the eager protocol and copy the message across immediately. If it's a large message, I'll send a little header. Does that make sense? The way to manually impose the eager protocol is to send small messages. You don't have, at least to try. Don't know if that's answered your question. But it's the receiver it's the sender that decides whether to use the eager protocol or not the receiver. Okay, thanks. Basically, okay, we're going over slightly. Collective communications, in your mind, a collective communication will have some algorithm where the collective is implemented by multiple sends and receives, and you should never write collectives yourself. You should trust that the MPI library is, has a efficient algorithm. However, there's nothing that mandates that the collective calls are implemented using MPI. So, for example, some modern hardware, some modern networks, and the Slingshot network is one of them, can actually do things in hardware. So, for example, the Slingshot network can do an all reduce in hardware. So when you call an MPI all reduce, it may not send lots of messages. It might just say, I'm on a network, can do that natively. So again, this is just basically saying you should always use collective calls if you can, because they will be implemented in MPI efficiently, or they may be implemented even more efficiently using tricks you don't have access to yourself. I've got a bit about collective algorithms here, but I'm not going to cover that because it's not really particularly relevant here. And this is, so I've skipped a few bits and pieces which you can look at later. They're not directly relevant to the exercise. They're really just comments. The one thing I will say here is that MPI is fundamentally based on send and receive. Its message passing. You have to transfer data from process A to process B. Process A issue a send and process B issues a receive. As I said just recently, some modern networks actually allow processes to read and write directly to each other's memory over the network. And so MPI exposed this possibility via things called put and get. So MPI2, which was found a long time ago, implemented a way where, at least at the software level, you can write directly to another process's memory. So you can do a send without there being a receive, called a put, and you can do a receive without there being a matching send. It's called a get. So in MPI, you can directly read and write to a remote process's memory. However, this is very difficult to implement, and in practice, these single-sided MPI put and get operations are not useful. I very rarely found them useful. However, what we are going to talk about at the end of the day is MPI. MPI extended this in MPI 3 to so this is saying I can directly read and write to another processor's memory who's on a different node. Okay, that turns out not to be very particularly useful. However, you might think to yourself, if two processors are on the same node, okay, why can't they directly read and write to each other's memory, as I could do in OpenMP? Well, MPI 3 extended this single-sided communication to allow you to directly read and write to another process's memory on the same node. And I think that is useful for both performance and memory reasons. So we're not going to cover single-sided MPI puts and gets, but we will cover a small part of that functionality, the part which allows you to read and write directly to another process's memory on the same node, on the same shared memory node, and we'll cover that at the end. And I think that is useful, which is why I still retain it in the course. So the summary, there's a lot of ways, there's many ways of specifying MPI communication: send, S send, B send. Should I use non-blocking? Could I use persistent? Which one is best or fastest depends on the implementation. Performance portability is therefore really hard, but what is often useful is to write simple benchmarks. We have a ping pong. I wrote a simple halo swapping benchmark. We'll do just around about lunchtime, and implement lots of different methods. And when you get onto a new platform, test all of them and pick the best. But what we're going to do is a slightly simpler example here. Is we're going to do a ping pong. We're going to do a very simple exercise where we send data between two nodes using send and receive, and from that we are going to work out what the bandwidth and latency is, and see if our theoretical model of these protocol messages and this eager and rendezvous protocol, can we see that happening in real performance figures from a real MPI library. So I will. We're a bit behind, but I did originally have a coffee break here, and I've split the practical around the coffee break. What I will do is I will basically just go through it. So if we go to the yep, trying to juggle too many windows here, I'm not doing very well. So that's the MPI course. I have a ping pong exercise sheet. So the way I, okay, I'm gonna have to now share. So this is the ping pong exercise sheet. Somewhere. So sometimes I do get, there we are. So there it is. Very difficult to find the right window. So this is the exercise sheet, you'll see that basically what it does is we have a program which sends a message between two processes. But hopefully you are able to just follow these instructions and get it running. So I'll just check. So I will just check with my own account before we do the before we take the coffee break that this works. So I will log in. Sorry, I'm going to log into ARCHER2 and then I'm going to show you my window. So I will now share this window and hopefully you will be able to follow these and play around a bit. So I am on ARCHER2 on my TA41 account. I've gone to /work, so I'm in the right /work directory. If I ls, I will remove this stuff because I was playing. Let's just check it works. You won't have that. So I'm completely clean account, but the most, as ever in Archer, you have to be in the work file system. So you have to CD to your work file system. Let us now see if I can. I would recommend that the way you get this is you just wget the file, and this should work. So if we do, we can now, oops, we now have the file here. So it's on the exercise sheet, you should be able to wget that file directly. I hate GitHub because it lies about what you have to mess around to be able to wget a file, but that's then I want to unpack it. And then I go into ping pong and then I just do make, and that will compile the file. And then all I do now is I do sbatch archer2.job, and that submitted the batch job, and it is now running. So you should be able to follow this. This if you look at the batch script, we are running in a reservation, okay, which is runs for this morning. If you're running on your own account, or outside of course, you'll have to delete these and you run in the short queue. But at least if you're using the TA241 account, I don't know if any of you, I see there's a few of us here. You may be on a different login node. That's run now, and if you look, it gives me this output. Okay, importantly, it prints out, I'll make this a bit bigger, okay. So running on two processes, same message between rank 0 and 1, but rank 0 is on core 0 of this node on this node. So I've got some code in there to tell you not only what node you're on, but also what core. Remember, Archer has 127 cores. There's some code to actually tell you what core am I on, which might be interesting. The important point here is, although I'm only running on two processes, they're on different nodes, okay? So this is sending data across the network. They're also right next to each other as well, two nodes. But this is sending data across the network. It runs lots of ping pongs, and it gives you the results here. That data. So you'll see that. Well, okay, it's giving you some results here, but actually it produces some files which you can plot. So in module load, I seem to have lost file system problems. Okay, good. It'll produce two diagrams, plot, bandwidth. This is and plot. And I will, so you should be able to, so what I will do is I will basically show you, only a bit over time, but I will show you these graphs just now, and then we've got time to run the example yourself, so we can discuss these later on. Apologies about this. Okay, so if you should be able to see these. If I share a window and I look at the, let's look at the time. Okay. You can see here, oh, there we are. That's what the benchmark does by send. And we can see here that for small message size, standard send and synchronous send have different times. There's a couple of wibbles here, and then later on they have at the same time. So what I would do is I would run this exercise. You should get a similar graph, but you can change things yourself. You can try different. You can try running them on the same node if you want. See what that does. See if you can generate this graph, and then we can discuss it after. We'll come back after the break and discuss it. The one thing I would say is you can ignore this point here. This initial point here is spurious. It's because for the very first time you do a ping pong, the process is maybe out of sync. So the very first ping pong you do takes a long time because they're not quite got going yet. So this is a spurious. I did rewrite the code to omit this point. It's surprisingly complicated. So this initial point is spurious. So you can ignore this. All the other ones are fine. This is a spurious point. This should be down here. So you can ignore that. That's a spurious result. Apologies. But after that, all these data points are consistent. So you can look at that, or you can look at the bandwidth, which is this one, which again is sort of the inverse. And we could then, so from the time graph, we can try and infer what the latency was. From the bandwidth graph, we can try and infer what the bandwidth is, et cetera, et cetera. So I'll kill these. So if I go back to my original time, slightly behind time, but I always had a, so I think what I will do is that at now have a break. We'll come back from this point-to-point performance and then go on to the next level. I'm going to take a quick break to have a glass of water and stuff. So I'm going to be back online at 11:35. But so that's the schedule now. I'll start lecturing at 11:45. But if you have a problem logging, I can help. But I'll be back online at 11:35. So sorry. I was going to just have a quick. So there's quite a few exercises on the sheet, but it is, I think, probably worth just going through in detail the basic. So if we look at this, we can see that immediately that this is going across the network, that we have a latency of about 1, 2, 3, there's about 4 microseconds. That's a microsecond there. So that's about the latency standard send is about 4. So that's a useful thing to know. It takes about 3 or 4 microseconds to do anything between different nodes. So we see that standard send, MPI has the choice to make it synchronous or asynchronous. For small messages, it makes it asynchronous. It uses the eager protocol. The reason that's faster than synchronous is synchronous has to have a handshake. So we might expect that if this was 4 microseconds, 1, 2, 3, this would be 8, 5, 6, that's not quite. But synchronous send is slower, and that's because synchronous send effectively uses the rendezvous protocol. You can also see the effect of the very short message. You can see that up to about 128 bytes, there's a jump from, I guess that's 128, maybe it's 25, is that 256? But we see there is actually a jump, okay? At the sort of 100 or so bytes, there's a jump. And that will be from the very short message protocol to the standard to the normal protocol. In other words, for the very short messages, it sends a little protocol message, a little header, and also has the data on it. Above that, it has to send the header and it has to send a separate message with the data. So this will be a jump here. I don't know why the jump is so big for standard. It doesn't really make a lot of sense, but that might be a glitch. I don't know, but there is a jump. Standard and synchronous, we see a jump in time. And so this is the very short message region. This is the eager. This is the standard, what you would call the eager limit, the eager regime, where the data is sent. You send a protocol message, you send the data immediately, eagerly, and the reason that synchronous send is slower is because you have this extra handshaking. Okay? However, above a certain message limit, there's something else going on here. Don't quite understand that, but a certain message limit, eager and standard and synchronous become exactly the same because standard becomes synchronous. Very large messages, standard has to use the rendezvous protocol. It can't use the eager protocol, so it effectively becomes synchronous. It's hard to see here where that happens. It's easier to see on the bandwidth plot. So if I show you the bandwidth plot, you can see possibly that actually it happens about, if I make this, I don't know if I can make this bigger. It's quite hard to see in a log plot, but it actually happens round about, there is actually a difference all the way up to about here. Now, the reason it's up at this large value here, if you looked up the manual for MPI, you do man MPI, I think. Okay. The point at which standard and synchronous become the same bandwidth, which is the point at which they use the same protocol, which is the point at which you exceed the eager protocol, is in the hundreds of kilobytes. Okay, it's hundreds of kilobytes up here. Okay, I don't know exactly what the figure is here, but it's several hundred kilobytes. However, this is why things can get a bit confusing. If you actually look at the manual, if I do man MPI and I look for eager, I get a few hits. But here we say, it says here that there is a variable here which buffer size, and it says that the eager limit is 16K. But we saw that the effect, the eager limit was in the hundreds of K, but actually it's even more complicated than that, because you'll see what MPI actually does on ARCHER2 is it breaks message into smaller units before transmission. So if you have a message of 100 kilobytes, it's broken into, say, 8 pieces each of which is maybe 12 kilobytes, that's below the eager limits. Each of those 8 pieces are sent eagerly. So it is quite confusing to understand what's going on often, because so here, for example, a simple model of there being just these two protocols, eager and rendezvous, is not enough, because actually there's another thing it's doing. It's breaking large messages into multiple small messages. So if you were to look at this graph, you would get a value for the eager limit, which is much larger than you get from the manual. But that's because this intermediate stage, where actually large messages actually broken up into multiple small values, multiple small messages. So things do get quite confusing. But hopefully, if I go back to this the one which I like, which is hopefully the simple model of eager and rendezvous and the very short message allows you to at least say that very, very short messages are fast. There's an intermediate period where standard send is faster than synchronous because it can use the eager protocol, and at very large message size they become the same. So that is, it's quite so hopefully that was useful. And there's more to do on the sheet, but that's the fundamental graph to understand is this time against message size, and the different regions corresponding to different protocols, and you can see that in the different times. And again, one thing I should say, if you look, the network bandwidth is up in the tens of gigabytes per second, right? So I said the latency was maybe a handful, 4 or 5 microseconds, and the bandwidth is up there at the tens of gigabytes per second. If you looked at the manual, that's kind of the numbers you'd probably get. So I just want any questions before I go on to the next, I went into the next lecture. So I'll do the next one, which is a slightly give me a second. I'm going to talk about how, I mean, this is kind of again, a slightly butterfly collecting in places, but how does this knowledge and what we know about MPI allow you to think about how you can optimize, write MPI, which is optimally efficient, which makes your code go faster. And what we're going to do is after lunch, we'll run a halo swapping benchmark, and we can actually measure some of these things in practice. So I'll go through this, quite a few slides. I'll go through this quite quickly, but please ask, because there's quite a lot here. You might be interested in one part, not another. There's not 43 slides. Quite a lot of these slides are hidden. But please chip in if you have any questions, like people did previously, were very interesting. So, I mean, there are 4 main reasons why an MPI program might not scale particularly well. And those are lack of parallelism, i.e. you have a serial part, load imbalance, some of your processes are more busy than others, synchronization, you spend a lot of time keeping processes waiting for each other, or communication, you spend a lot of time actually sending data. And originally this talk went through all 4 in detail, but I've changed the emphasis to be much more about synchronization and communication. But I will cover the first 2 very briefly. So this is really a more general topic. You've got a code which doesn't scale particularly well. What could be the reasons about it? And so, for example, lack of power, the obvious thing. Tasks may be idle because only a subset are actually computing, and the classic ones are in general work done on task 0 only. So you have, if you have some computation you've not got the ability to or haven't had the time to parallelize, and that is done on task 0 only. And really the only cure there is to redesign the algorithm to exploit more parallelism. In practice, this is often due to I/O. The naive way to do I/O is to have the I/O done by a single rank, often rank 0, and there you'd have to parallelize your I/O. There are ways of doing that, but that's quite, well, MPI/IO, there are other libraries, NetCDF, HDF5 that allow you to do that. So in practice, in a real program, the times you see a lot of programs where you see spend a lot of time where only rank 0 does work is often in I/O. Load imbalance, all tasks have some work to do, but some more than others. This is really quite a difficult problem to solve in distributed memory. And shared memory in OpenMP it is relatively straightforward because all the data is there in shared memory, and there are actually directives in OpenMP, dynamic scheduling, and there are ways in OpenMP natively to help your load balance, such as dynamic scheduling. The problem with message passing in MPI is that when you move the work, you have to move the data. So if you want another process to take over the work, then you also have to move the data. And so this can take significant algorithmic changes, and often the load balancing algorithms themselves aren't particularly parallel. So the load balancing algorithms may scale as they may take longer on more processes. So load balance in solving load balance in MPI when it's an algorithmic issue is really quite difficult. And so that is, I'm not going to cover that here. It is a big challenge. It's often used to be able to spot load imbalance, though. Okay, even if it's useful to know you have it. And so you may run your program under some MPI profiling tool. There are generic ones, or we have CRAPAT on ARCHER2. And load imbalance is due to different processes having different amounts of calculation to do. But in practice, when you do a profile, this may show up as communication. Okay, so if you run an MPI profiling tool on a program which has load imbalance where you haven't successfully balanced the the calculation, what you will see is a lot of time in communication. Now, what this often means, and we'll come back to this later in the talk, is that a process has issued a receive after doing some work. It had very little work to do. It issues a receive, so it spends a lot of time in the receive waiting for the other processes to catch up and do their send. And so the task is blocked, waiting for another task to enter the corresponding MPI call. And so tracing tools often show up load imbalance very clearly. Running tracing tools can be an overhead in themselves, but it's very important to note that what is actually a load imbalance in the calculation of your code will often show up as a lot of time spent in communication. So it can be quite confused. People often say, all reduce is very slow. It takes an awful lot of time to do an all reduce. That may not be true. It may be that all reduce is having to spend a lot of time waiting because processes are entering the all reduce at different times. So synchronization, this comes back to saying synchronization in the message passing code wastes time. And in MPI, most of your synchronization is coupled to communication. If you have a blocking send or receive, if you issue a receive, you have to wait for the data to come in, so there'll be synchronization there. You also, even if you do non-blocking send and receive, at some point you have to do a wait on the request. So you are always at least some point saying, I cannot progress until this communication has completed, and that will require synchronization between processes. And collective communications are mostly synchronizing as well. For example, a standard one is an all reduce. When you call an all reduce, it's not possible to complete an all reduce until all processes have entered, because all processes have input and receive the output. So the important point here is your canonical model of a load imbalanced program is one where some of the processes have more work to do than others. For example, you may be doing a weather model, and some of the processes have land, and some processes are doing the weather over the sea, and it takes different amounts of time to compute the weather over the land and the sea. In practice, what can happen is that if you do too much synchronization, you can waste time, because even if you, in principle, your program is load balanced. So you may say to yourself, my program is load balanced, all processes have the same amount of calculation to do. So if they have synchronization to do, it doesn't matter, they'll be ready for each other. In practice, modern computers don't run, two processes, two nodes don't run at the same speed as each other, even if they have the same amount of calculation to do. That's because modern computers are very complicated, and you have an operating system there. So for example, you will have random noise. You run the same program twice in a row, and different processes will take different amounts of time. And the trick is, because you don't know how long a process is going to take, relative to another one, you should do as little synchronization as possible, because every time you do synchronization, you're amplifying that random noise. And a classic reason for random noise is OS interrupts. The operating system has to go away every now and again, check for I/O and bits and pieces, and ARCHER2 will have that tuned down to be as low impact as possible. But your process is doing a lot more on a modern computer than just running your program. And so the trick is to avoid unnecessary synchronization, because even in a program where in theory, in principle, it's load balanced, in practice at runtime, different processes will take different times to run, and you don't know which process is going to be slow because it's effectively random each time you run the program. And so there are simple things you can do. The classic one is that you're using an OR reduce to compute some termination criterion. So your standard algorithm on the left, you're looping over many iterations, you're updating a bunch of arrays, you're computing and what you're doing is you're basically saying, I've got an algorithm where I will stop when the change, this delta I'm computing here, is small. So every single iteration, you update your arrays, you compute the local change, you do an OR reduce to compute the global change, and you stop if that is less than some tolerance value. So running an iterative algorithm with some termination criterion, which is computed via a global reduction, an OR reduce is fairly standard. If that is the format of your algorithm, then what you can sometimes do is you can actually basically only do the check so this can potentially take a lot of time, okay? You can do the check infrequently. You can say, oh, well, I will only check for termination every 10 iterations. And if you do that, that can have an advantage, because although in principle you might, if I only check for termination every 10 iterations, even though in principle that might mean that my algorithm might run for 9 extra iterations, if I'm doing it for millions of iterations, I save time. So if the OR reducers are taking a lot of time, you can do something which might make you feel a bit unclean, but you can basically only check periodically. Now, this is only possible in very simple algorithms. It's possible because this global delta is just a diagnostic. I'm just calculating it. It's not factoring in to the actual update of your data. Now, in a real algorithm like like something like conjugate gradient, the results of your global reductions actually you can't delay them. But there are cases where if you're doing an algorithm where there's minimal communication required in the update of the arrays, you can if you're just using a stopping criterion, you can check for that infrequently, and that can be a useful thing to do. This is one of my, it's like bugbears, but barriers. A lot of MPI programs have barriers in them. Barriers are, I would say, they're almost never required for program correct. You can write correct MPI. You can write MPI programs where they are only correct if you put a barrier in. However, they have to be incredibly contrived. So in practice, a real MPI program, if putting a barrier into your MPI program changes it from being a correct program to a non-correct program, or the other way around, you've probably got a duff program. Okay? Real MPI programs don't need barriers for correctness, because the collectives do the appropriate synchronization, or MPI receive it. So you sometimes see people say, I'm going to do an OR reduce, I'll do a barrier to make sure everyone is ready. You don't need to do that. When you call a reduction operation, the reduction operation, the collective, does all the appropriate synchronization. When you don't have to worry about about the ordering of sends and receive, because if the MPI receive is posted early, it will wait for the message to arrive. And so the first optimization technique you can do in almost any program is take out all the barriers. But then that's okay. So I'm going to talk a bit about the overheads of inherent in communication. And I'll talk about point-to-point mainly, and then a bit about collectives. Hopefully I'm back alive again. I had a glitch there again. Okay, so I'm mainly going to talk about point-to-point. The terminology I'm going to use here and the concepts I'm going to cover are equally applicable to collectives, but the point-to-point is a much more interesting theater to talk about them. So we've talked about this already. I used my my car analogy, where it takes you a finite amount of time to walk to the garage, and then once you've done that, you get in your car, you drive at a constant speed. The same is true on the point-to-point messages. In a point-to-point message, we can model the time. We've really covered this already. It's the time for the communication. It's the latency plus well, we'll talk about here. The time is the latency plus the number of bytes divided by the bandwidth. So we've talked about that already, and we've measured the time, the latency, and the bandwidth on ARCHER2. The latency is a handful of microseconds. The bandwidth is in the tens of gigabytes per second. If you think about it, that means the latency is quite high. Latency is relatively large. Microsecond might sound like not very much, but remember that your processors are clocking at a multi-gigahertz speeds, so the clock frequency is in the nanoseconds. So the most important thing here is it's faster to send one large message versus many small ones. So you should never do lots and lots of small sends. You should do one send of a large message, and that's for point-to-point. That's fairly obvious. It applies to collectives. An overall use of 2 doubles is about twice as quick as 2 overall uses of 1 double. So if you have multiple overall uses to do them in one call. And you might say, well, I need to do multiple MPI calls because I have integers and doubles. You can use derived data types to send messages with a mix of types. So if you have small messages, okay, then you should try and aggregate them. And there's various techniques for doing that. What I'm going to talk about here now are various standard communication patterns which arise in real programs that lead to poor performance. And so we're going to talk about, this is not OO design, it's communication patterns between different processes. And we're going to identify with a few diagrams a number of standard patterns of communication which can be the cause of poor performance. You might be able to identify these by eye, or they could be discovered automatically through a tracing tool. There are some tracing tools such as Scholastica, which actually try and identify these. So the Scholastica tool is an open source tool produced out of the Jülich Supercomputing Center in Germany. And it is a tracing tool in that it monitors the performance of your program and instruments the MPI calls, but it also tries to attribute meaning to that. So it can say your program spent, we'll come back to this, but it can actually say your program spent a lot of time in receive, and I think it was because of this issue. And so this terminology is quite commonly used. So I'll go through these patterns quite quickly. So a classic one is a late sender, okay? So if you do a blocking send, so that could be synchronous send, or it could be a very large standard send, which is above the eager limit. If you do a blocking send, then the receiving task must wait. Sorry, I got this the wrong way around. Okay, so so time is going from left to right here. We have a sender and a receiver. A late sender, go back to the part, is when a receive has to wait on the send. So you've issued a receive and you're expecting a message, but the sender is coming in late. And so the receive has to wait until the send happens. And so the receive takes a long time before the send is posted. So if you ran a tracing tool on your program, you would see a lot of time spent in MPI receive. It might not be obvious why that is. A tool like Scholastica might be able to say you spend a lot of time in MPI receive, and it is because of a late sender. It may be able to also see that is due to sends being issued late. But a late sender is a lot of time in a receive because the receive is posted early or the send is late. You can also have late senders because of out of order receives. So, for example, you're expecting a message from these two ranks. You issue this receive first, which is coming from, you issue this receive first, which is coming from this send. Okay, so this send happens first, but you issue the receive for this send first. So when you issue this receive, although this send has already been issued, you're waiting for that send there. So you spend a lot of time in the receive, and then you issue the receive from here. And so you've got a late sender here. This receive is waiting a long time for that send to come in, or alternatively, that send is late with respect to this receive, but actually you've issued to them in the wrong order. So what you probably ought to have done is issued the receive from this process first and this one second, and that would have given you less of a time spent in receive. Now, if you had a deterministic program where it might be quite obvious to spot this, in practice, you may have out of order receives. You may be issuing receives for sends which have not yet been posted, but other sends have been posted. However, that may be non-deterministic, because in practice, this is because it happened to be that this time you ran your program, that this time you ran your program, this send was late, but the next time it might be the other one that's late. So although out of order receives is an issue, is a problem, it's very difficult in practice often to predict what the order will be. And so we'll come back to this in a few slides, but the important point here is not to impose an ordering on the receives. If possible, don't impose an ordering, allow them all to happen at the same time. And that can be done through non-blocking communications. A late receiver is the inverse of a late sender. If the send is synchronous, as I said, either because it is explicitly a synchronous send, or it's because of a send of a large amount of data where you can't do the eager protocol, then you spend a lot of time in the send waiting for the receive to be posted. And again, yeah, that's a standard thing. So the receive may be waiting on the send, or the send may be waiting on the receive. So I've talked about this already, but I'll come back to it. MPI, this is where MPI progression, how MPI actually works internally, can have an effect on performance. As I said, your mental model of MPI is that it runs continuously. So, if you do asynchronous or non-blocking communications, people often say they happen in the background. So your mental model is, if you have either asynchronous or non-blocking communications happening and calculation happening, they happen at the same time. You think of communications and calculation overlapping in time. This is generally not true, okay? Although the MPI library is typically single-threaded by default, communications can only be processed when your program calls an MPI function. I mentioned this before. So what that means is, in practice, MPI treats every call to the library as a kind of a manual interrupt. And it will try and progress communications by match. So when you call any MPI routine, the first thing it does is goes away and does lots of bookkeeping. And actually, if you download an open source MPI library, you will see the code for something like an MPI receive is incredibly complicated, because the first thing it does is it goes around and does a lot of other stuff before it ever issues the receive at all. So if you issue a non-blocking send, okay, it may be sent immediately if there's an existing receive. Your mental model is that this happens in the background until the receive, that this happens in the background. But so it's either sent immediately if there's an existing receive. If not, it cannot be sent to the next explicit MPI call. However, that may be unrelated to the outstanding communication call itself. So what this is saying is, if you issue a non-blocking send, it may be sent immediately if there's an existing receive. If there isn't, the next opportunity MPI has to send it is when it's in the MPI library, which is the next time you make an MPI call. So this can be really quite difficult to diagnose. So what happens here is, you issue a non-blocking send. At this point, the receive hasn't been issued on this process here, okay? And so the data isn't sent. Later on, you may issue another MPI call, which allows MPI to go away and progress existing outstanding communications. And so this ISEND may be completed here. However, the completion of the ISEND, the non-blocking send, may have been triggered by a receive call on the sending process. So any MPI call on the sending process allows MPI to progress stuff that's sitting around locally. And so a receive on a process may actually trigger a send. So the send is delayed until the MPI library is re-entered by the sender, and that re-entry into the MPI library could be through a completely unrelated call like a receive. So this again can be quite difficult to diagnose, but again, I think that the basic fundamental message here is that the ordering is complicated. Sorry, the order you do things in MPI can affect the speed of your MPI calls, that you don't quite know what the optimal order is. So where possible, you should try not to impose an ordering. So as I've said here, you may say that your program doesn't have load imbalance, but in practice it does, because random noise. And so not only can two pieces of calculation not take the same amount of time because one of them may be interrupted by some operating system interrupt, it may not take constant time to send a message because the network may be congested. Remember, you share the network, such as the Slingshot network and ARCHER2 with lots of other users. And so I've been going around the houses a bit, but it can be better to avoid delays by using all non-blocking comps entirely. Okay, so because you don't know what order the messages are going to be sent or received in, and because you can't predict what that is, the best thing is not to prescribe any ordering whatsoever. And so what you should do is, if you have a bunch of sends and receives to do, you should issue them all, issue all the sends non-blocking, issue all the receives non-blocking, and then wait on them all to complete. And that allows for MPI to complete them when they're ready. You should not impose an order saying, do this send, do this send, do this send, do this send. You should tell MPI, I've got a whole bunch of sends and receives I want to do, and I want you to wait at the end until they're all over. And that's what the Halo benchmark hopefully demonstrates in practice. So that is, I've gone around the houses a bit here, but basically it can be beneficial to avoid delays by using all non-blocking comps entirely. Lots of I sends, lots of I receives, and await all. And I'm going to illustrate that by imagining a sort of a Halo swapping routine. We have a standard sort of update algorithm, which is the 5-point stencil. The new value depends on the old value and its 4 nearest neighbors. And we implement that by using a Halo swap to have standard code, which we have. This is our local data. We extend the data in all the dimensions by 1, so we can have a Halo. And before we update the data, we do a Halo swap, where the boundary data from the neighboring processes is put into my Halo. So this is a standard parallel pattern. Before doing any computation, you swap Halos, apologies, with your neighbor, and then you can do the calculation. Sorry, I'm having some slight problems here. Apologies about that. Okay. So you should you should not impose unnecessary ordering of messages. So what you should not do is receive the Halo up, receive the Halo left, receive the Halo right, receive the Halo down. You should try and have all the Halo swaps going on at the same time. You could try and do that by, rather than looping over the sources and receive from a particular source, use wildcarding to loop over source and receive the value from any source. However, in practice, rather than using wildcarding, it's better to use non-blocking communications. And so the best alternative in practice, first issue a separate non-blocking receive for each source, then issue a single wait all. It's actually also best to probably do the sends and receives, doing the sends non-blocking. So Blair's asking if I create too many I receives at the start of your program would run into issues if raw buffers required. So first of all, I'm thinking about this being in a tight loop, and so typically you know how many receives you have to do. In this example, in a 2D simple Halo swapping example, we have 4. In 3D, it might be 6. So typically you don't have a huge number of outstanding receives. Also, remember when you issue a receive, maybe I'm misunderstanding the question, but you specify the receive buffer. So you have to have allocated the space for a receive. So it's, yes, in principle, if you have lots and lots of receives at once, you have to have buffers for all of those. But they're allocated by you. The receive buffers are allocated by you. I don't know if that answered the question. Yes, in principle, but I'm thinking about it. So for in this Halo swapping example, I already have pre-allocated all the receive buffers. My receive buffers are the Halos. They've been allocated at the start. They're always there, and I'm just altering what order I receive data into them. So in this case, I'm not actually, although I've got lots of I receives active at the same time, I'm not actually having any more received buffers. They've already been pre-allocated as my 4 halos. Yeah. So what people often do is when they do halo swapping, they loop over directions. They say, well, halo swap in the up-down direction, then halo swap in the left-right direction. Okay, that is not the best thing to do. Again, you're imposing an ordering. You're saying, when you're saying, if you say I want to receive halos in the up-down direction first, then the left-right, you start receiving data in the up-down. Maybe the left-right halos were already ready. So the trick to do that is to have no ordering at all. Don't loop over direction, send up, receive down, send down, receive up. Issue all the non-blocking sends for all the directions at once, and then wait on all the requests. So what you're doing here is, here we have 2 directions, and we have I send and I receive in both directions. So we have 8 outstanding non-blocking communications. So what I am saying here is my advice would be, and hopefully this is borne out by the actual results from the halo swapping benchmark, is that the most efficient way to do this pattern is to issue all 8 sends and receives at the same time. Send up, send down, send left, send right, receive up, receive down, receive left, receive right. Issue all of them in a non-blocking way, and then do a wait all on all 8 requests. And so that, I think, is the right thing to do, and hopefully that will be borne out by the benchmark. What people now say is, okay, what I can do is, while I am issuing the sends and receives for these halos, okay, for these boundary swaps, I can process the internal region here, because this doesn't depend on the halo data. So people think, okay, what I will do is I will post off all my halos. I will do all the calculation which doesn't depend on the halo data. Then I'll wait for the halos to be received. Then I'll tidy up, I'll finish the outstanding computation which depended on the halo data. Okay, you see this a lot of codes, people trying to overlap communications with the core calculation. And so what you do is you issue lots of non-blocking sends and receives. You don't loop from 1 to M and 1 to N. You loop over this interior region here, this white region where the results don't depend on the halos. And then you wait for the completion of non-blocking sends and receives, and then you complete the calculation of the 4 edges. That's a standard pattern you see in lots of codes. And mentally, you think this is a good thing because you think the non-blocking sends and receives can happen in the background while I'm doing my core calculation. In practice, I don't think that normally works, okay? This may not have the benefit you expect. The messages are probably not transferred in the background. They're either transferred when the send is issued or delayed until the wait all. Or they're sent immediately because you're using the eager protocol. And so in practice, I see a lot of codes that have this overlapping built into them. My suspicion is that a lot of them, it isn't actually benefiting performance. It may benefit performance, it may not. That depends on the network and on the particular details of the computer you're running on. This is also a more complex code if you separate it out into this 2 phases of communicating the core calculation, then tidying up at the edges. That's the code is more complex there. The code complete calculation can result in nasty code. It can be less cache friendly. So my basic advice is, you're welcome to go away and implement an overlapping version of your algorithm, but always maintain a non-overlapping option in your code. When you go and run on a new platform, check that all this extra code you spent weeks and weeks putting in actually helps you. So often the naivest and most straightforward code can be the fastest, because the additional code complexity can outweigh any performance benefits. So you can also use persistent communications, as I said here, rather than pre-posting, rather than every iteration of your loop issuing the sends and receives, you pre-define them all, and then you do a start all and a wait all. Again, this is one of the options in the benchmark that we'll run. In practice, as I said, it doesn't actually help in practice because you don't save much time, but I benchmarked it just because I wanted to check. But in principle, MPI could do optimizations here because it knows you're going to be running the same calculation thousands of times. The same communication thousands of times. In practice, if that communication is just a send or a receive, there's not much optimizations to be done. So it's not a big deal. This is slightly outside the scope of the course, but I did want to mention, because it's in the benchmark as well, there are a new set of collectives called neighborhood collectives. A standard collective operation applies to the entire communicator. So if you do an MPI on reduce on MPI com world, then every process is involved. Neighborhood collectives only apply to your neighbors, and that requires you to define a Cartesian topology or a graph topology, but it's simpler to think about Cartesian topology. And a neighborhood collective then doesn't imply communication between every process in the whole communicator. It implies communication between every process, and in 2D it's 4 nearest neighbors, in 3D it's 6 nearest neighbors. The bottom line is, it is possible to do halo swapping in an n-dimensional regular grid with a single collective call. It's called MPI neighbor all to all W. Again, it's slightly outside the scope of the course I'm doing now, but I wanted to mention it because it's in the benchmark. So if you're interested in writing a really cool program where your rather complicated halo swapping code is replaced by a single call to one MPI neighborhood collectives, you're welcome to go away and do it. However, if you run the benchmark, you'll see that in practice, it's probably the same performance as doing it at point-to-point communications, but it's an option. And so MPI neighbor all-to-all is this collective communication which allows you to do halo swapping in n dimensions with a single call. The code is more elegant and more compact than point-to-point. It's hopefully done. In practice, it's not many more efficient, but I'm just mentioning it there because it's something you may see in more modern codes. We can identify all the same patterns, late sender, late receiver, and such like, in collective communications as we can in point-to-point. But I won't go through them all because it's really fairly obvious. If I think about, for example, if you think of a late broadcaster, if you've got a broadcast, okay, then if the person issuing the broadcast is late, all the other tasks have to wait. Okay, and actually you do see this one an awful lot, because often what you're doing here is you're broadcasting data on the root process that you have read from file. So what this lag time is, all the processes other than the root process are called the broadcast. The root process is doing read data in from file, then called the broadcast. Now that probably can't be avoided, but that's often where you see it. And there are other early reduce, all-to-all, and I'm not going to go through them all. But again, because collectives imply synchronization in almost all cases, if all the processes don't call the collective at the same time, you end up spending a lot of additional time in them. I say collective comms are hopefully well optimized for your architecture. They are expensive and force synchronization. As we've said, if you can, possibly a simple way of saving time is to do it less often. Okay, that may or may not be possible according to your algorithm. There are non-blocking collectives available. Okay, so I said that the way to avoid additional synchronization overhead in point-to-point communication is to use non-blocking calls and do as many of them as possible. There are non-blocking collectives in MPI where you can, rather than saying do this or reduce, you can say please start doing this or reduce, and I'll come back later and get the result when I need it. In practice, I have very, very rarely seen any benefit from non-blocking collectives. Most algorithms need the result of the or reduce. If you look at something like conjugate gradient, you do a local dot product, you need the global sum of that dot product, you need the answer on the next line of the algorithm. So in practice, although non-blocking collectives sound like a really great idea, in practice they're typically not that useful, in my opinion. So the general advice is try to avoid imposing any non-essential message ordering, because when the messages are actually sent, is not predictable. So any ordering you impose may be right one time and wrong another. Try to allow MPI to deal with messages as they happen. In practice, this means issuing all your sends and receives as non-blocking. Again, you should issue the receives as early as possible. So if you can post the receives at the end of the previous iteration rather than the start of the new iteration, that might help, because when you post your sends, the receives are already there. And so you don't get this problem that you have unexpected messages coming in. If you can post the receives first, that's a good thing to do. You could try setting up persistent or use neighborhood collectives. Final thing is avoid unnecessary calls by, this is a new comment I've put in, which is why there's a typo here, which I will fix. Sorry, apologies about that. I'll fix that. Avoid unnecessary collective. So the two ways to avoid unnecessary collective calls are: don't do them every iteration, do them every 10 iterations. That may or may not be possible depending on your algorithm. Another really useful one is do one all reduce of 3 doubles, not 3 all reduces of 1 double. An all reduce of 3 doubles will be 3 times quicker than doing 3 all reduces of 1 double, because when you do an all reduce, the time is not in transferring these tiny amounts of data or in adding up tiny amounts of data. It's in the global synchronization and management of all those processes. And the final is, do I really need any of those barriers? I've almost never seen a code where the barriers where an MPI barrier is required for correctness. So as I said, we've summarized these are the overheads of where MPI programs run suboptimally, and in practice, synchronization is the one that you can actually more easily attack. And a lot of programs I see do halo swapping or some kind of boundary exchange like that, and they do it in a fairly predictable, prescriptive up, down, left, right way. I don't think that's the best way to do it. That would be my first advice, is to do that all in a non-blocking way. And hopefully the benchmark we're going to run, the halo swapping benchmark, will allow you to see the implications of that in practice. So I'm just about back on time. If I go to so I had to reboot, so I've lost some of my bookmarks. I share. So hopefully you should be able to see, yeah, there we go. So the plan was to do, yeah. So, okay, so the way I've done it now is that, okay, so we're going to do the practical before lunch, okay. So the idea now is to do the halo swapping practical. Yeah, the halo swapping practical. And so I will, if you look at it, the 3D halo swapping benchmark is something which I have put up on GitHub, but what it does, and so I don't have an exercise sheet here, there's a README on the file, is it sets up a 3D array of processes and swaps halo data up and down in all 3 directions. So basically it's trying to mimic a simple program, which is a 3D parallel decomposition of a 3D problem with nearest neighbor halo swapping in each direction. And now this code is written in Fortran for historical reasons, but hopefully it should be sight readable even if you're not a Fortran programmer. It uses a whole bunch of different approaches. It uses pairwise swapping, each dimension in turn using MPI send receive. I haven't had a chance to talk about this, but I recommend breaking deadlock in an MPI program using non-blocking communications. There is a lot of programs you see use send receive. So if you want to do halo swapping with send receive, you have to loop over each dimension using send receive. The next one is to break the deadlock by splitting the processes into odd and even subsets. So I've called these red and black. The red processes send first and receive second. The black processes do the opposite. That's another standard approach I've seen. So what I've done here basically is implement every approach I've seen in real codes for 3D halo swapping and see which one is the best. Another is pairwise swapping in each dimension using I send, receive, and wait. Pairwise swapping each dimension using I receive, send, and wait. Pairwise swapping each dimension using I receive and I send. Then the one which I think is going to be the best is non-blocking comms in all directions and a single wait all. So this is where I'm saying we've got 3 dimensions, up, down halos in each dimension. So that leaves you with a total of 6 sends and 6 receives, or 12 non-blocking communications. I've implemented that. I've implemented persistent communications, and I've implemented neighborhood collectives as well. But the benchmark is kind of a standalone benchmark that just runs all of these. So you're welcome to look at the code if you want. There, the code is hopefully reasonably, it's my code, so it's pretty naive. But for example, you can look at you can look at the code if you want, but this is what it does. We can run it and see which is the fastest. Now, this is the kind of program which, I mean, I know what the results are on ARCHER2, but hopefully this will be interesting to run on your own, on other machines, and see if these results are consistent. But my assumption is that this will be probably the most efficient by a reasonable margin of these halo swapping. So you should be able to download and run the benchmark. I think I've automated it all. The one thing I would say is that the code does the whole benchmark 3 times. The reason is we found that certain MPI routines do a bit of setup the first time you call them. So I was getting inconsistent results. The very first iteration you run, it may be the first time you've called a non-blocking a neighborhood collect. It may go in. The first call to an MPI routine can be slower than all the other ones. So I run the benchmark 3 times. I would suggest you ignore the first 2 runs and just look at the results from the 3rd run. You can compare them, but if you want to look at one set of results, look at the result. It just says I'm doing run 1, run 2, run 3. Within the program, it runs it 3 times. And so let's just check that this does work as expected. So the other things I've said here is you could change the buffer sizes to be small or big. There's more than one way of doing MPI. At the lowest level on ARCHER2, you can use something called the use protocol. You can try that, but I will expect it. So let's share the right. And then I'll let you run it, and then I'll maybe summarize the results just before we take a break for lunch. So let's just give me a sec. So if I now do git clone, I go to Halo Bench, I should be able to make, it's make -f make file ARCHER2. Apologies for that. Apologies, my Fortran isn't particularly good. There's a few warnings to do with my modules not being particularly well constructed. And if I sbatch, actually do a job. SQUEUE. Fine. So you should. So it does seem to work. You should be able to run that. The code doesn't take that long to run, but the issue on ARCHER2, the MPI jobs are taking about 20 to 30 seconds to start up on nodes. 30 seconds. It hasn't really been. It's basically a lot of that was stored, but it. Still running. Yeah, so the Halo Bench is running. So it's running yet. Hasn't quite finished yet, but okay. So yeah. So it's still running. It's taking longer than I'd expected, but it's completing now. So you should get. So if you look at the output you get, you'll see lots of figures. And what we can do, I mean, so I'd like you to run that. Maybe I'll look at it, and then we can come back in about. What I'll do is I'll summarize those results after lunch. Actually, that's probably the best thing to do, given it was slightly later than I expected. And with what I will do is. So probably that's the plan. So I would say, yeah, I plan to summarize the Halo bench before lunch, but I think because we're running a bit late, I'll do it. So my plan, hope is that you can get that code. It seems to check out, and I was running there as not as myself. So if it works for me as that user, it should work for you. You should be able to run the Halo bench. We'll take a lunch break 1 till 2. I'll start lecturing again at 2, but I'll go over the Halo bench results for 5 to 10 minutes before doing the lecture. The main thing, I'll be online until 1, then back at 2 p.m.